Hi, this is Mrs. LaBarbara. This is AP Physics Mechanics C. Today I want to go over an example of conservation momentum and energy. A student sets up an experiment with a cart on a level horizontal track. The cart is attached with an elastic cord to a force sensor that is fixed in place on the left end of the track. A motion sensor is at the right end of the track as shown. The cart is given an initial speed v naught equals 2 meters per second and moves with this constant speed until the elastic cord exerts a force on the cart. So the motion of the cart is measured with motion detector, and force of the elastic cord exerts on the cart is measured with force sensor. So both sensors set up so that positive direction is to the left. The data recorded by both sensors are shown above in the graphs of velocity as a function of time and force as a function of time. Calculate mass of the cart. So let's take a look. From force versus time graph, we know the area. This area is the impulse. Impulse equals to change in momentum, or mass times change in velocity. From velocity versus time area, we can find the change in velocity. So from there, we can find mass. So mass equals to 0.25 kilogram. For the time period from 0.5 seconds to 0.75 seconds, the force F the elastic cord exerts on the cart is given as a function of time by this equation, F equals A sine omega t, where A equals to 6.3 Newton times second and omega equals to 12.6 radian per second. Use the given equation, show that area under the graph over here is 1 Newton times second. So how do we find area? Area actually equals the impulse is the integral of F times dt. And what is F? F is A sine omega t. So A is 6.3, omega is 12.6 times t. The integrate of this, remember integration is antiderivative. So the antiderivative of sine is negative cosine, hence the negative sign here. Another thing, because the chain rule is kind of inverse of the chain rule. For chain rule, you multiply. When you integrate, you have to divide. So you use 6.3 divided by 12.6. That's divided by omega and change sign to negative cosine. Next, you substitute the top number, then minus the bottom number. So remember, this has to be in radian mode. If you put in your calculator, you should have 1 Newton times second. Part C. The experiment is repeated using a different cord that exerts a large average force on the cart. The cart starts and ends with the same speed as those in the original experiment. Will the area for the graph of the force as a function of time for the new cord be greater than, less than, or equal to the area of that of the original cord? Justify your answer. So let's take a look. What does the area of force versus time represent? It represents impulse. What does impulse equals to? Change in momentum. Did the momentum change? No, it didn't, because the car starts and ends with the same speed. Since momentum did not change, the impulse does not change. So the area shouldn't change. So it should stay the same. So the area will be the same because the area equals to the change in momentum, and change in momentum is, there's no change in momentum change equals to 0, so the area has to be the same. What is different now? Now the force is bigger, so your time is shorter. So the shape of your graph is different, but total area is the same. Part D. The elastic cord from the original experiment can be modeled as an ideal spring with a force constant K. Derive an expression for the maximum change in length X max for the cord. Express your answer in terms of mk, v naught, and physical constants as appropriate. So this is energy conservation. Originally, your card has kinetic energy. Then as card moves, the cord is stretching it until the card stops. At that moment, all its kinetic energy has converted into elastic potential energy. So UEL equals to K. So from this equation, you can find X max. Now the student performs several trials of the experiment. For the first trial, the cart is empty. In each succeeding trial period, a block is added to the cart. In all trials, the cart has the initial speed of 2 meters to the right. The cart rebounds to the left with a speed of 2 meters per second. And the maximum change in length of the elastic cord is measured. Total mass m of the cart and the maximum change in length of the cord each trial are recorded in the table. So basically, you're changing the mass and you record elongation. Part E, indicate which quantity should be graphed to yield a straight line with a slope that could be used to calculate the numerical value of the force constant of the elastic cord K. What is the horizontal axis? What's the vertical axis? Then you can use the remaining column in the table to record whatever you need. So let's go back to the equation. X, the elongation should relate to m in this relationship. X equals mv naught squared over k. This is what we got in part C, I believe. So when we change the mass, x change. How is x related to m? X is proportional to square root of mass. So this is a direct relationship. Direct relationship gives us a straight line. So what's your x? Horizontal axis should be square root of m, and your vertical should be x. You can say, I can square both sides, then this would be m, this can be x squared. That's fine also. So then your data table over here would be x squared. But I've chosen this way. The other way is not wrong at all. Okay, so I'm going to graph square root of m, or x max versus square root of m. So I do the square root of all this column, get my data. Next part is to plot the data. Remember, you'll have to clearly scale and label all axes, so the scale has to be linear, and you're asked to draw a straight line that best represents data. So the scale for a square root of m is from 0.5 to 1.5, and I find this way is the most convenient way to graph it. And for your x max is from 0 to 0.5. Remember, you have your units. Make sure you label your axis. Next one is carefully put all the points on the graph and then draw the best fit line. So your best fit line again should be close to all the data and should have some points above and some points below. Last part, use the best fit line to calculate the force constant K of the elastic cord. So let's take a look at our graph. Here is the graph. We have to use this best fit line, mostly the slope. Let's go back to the equation. X equals to this times m. So the slope equals square root of v naught squared over k. If we find slope, we can find k. Let's square both. Then we can change the position of this two. So k equals v naught squared divided by slope squared. To find the slope, you need to choose 2 points on the line. So you look at this point, maybe this point. Those are good points, easy to read data. So a slope equals to change of y divided by change of x. Make sure you have your units. Slope equals to 0.33 meters divided by square root of kilograms. Now you have the slope. You can go back to this equation to find k. K equals v naught squared divided by slope squared. V naught, we're given V naught is 2 meters per second squared divided by that. You should have 36 newtons per meter. Make sure you have your units. And that's it for this question. Thanks for watching. See you next time.